As you can remember, on our previous lesson, we have learned something about electrostatic field, and we have learned that electrostatic field that produced by system of point charges can be calculated with formula. Can be calculated with formula that can be written in this way. Electric field intensity is equal to 1 divided by 4 p epsilon 0 sum I is equal to 1 n q I divided by modulus of r minus r I in third exponent. Insert exponent and r minus ri. We can use this formula to calculate electric field intensity that produced by system of point charges qi. And when there is space distribution of charges, when charge is distributed in space with charge density, this formula will look like integral, volume integral, and sometimes it is difficult to calculate this space integral, but in some cases it is possible to use another way to calculate electrostatic field, and we will learn this today. I mean Gauss law or Gauss flux theorem. To learn this, we have to consider a new physical value that is so-called electric flux. Electric flux. What is this? Electric flux. Electric flux. Electric flux. Electric flux is surface integral. I hope that you can remember from calculus what surface integral is. Surface integral of electric field intensity ds. It can also be written in another form. It can also be written like this. Surface integral S E multiplied by n, where n is odd, the surface S, and it can also be written in this form. En ds. En is a projection of vector E on perpendicular to the surface direction. It is a projection of electric field intensity vector on the direction that is perpendicular to surface S. This is electric flux. This is electric flux. New physical value that we have learned. And why do we need this value? Maybe it is necessary to give some explanations about this name, electric flux. Why is it called in such way? It is called because it is a formula similar, because there is similar formula for the case when we have, for example, if we have net in front of water, water float, with velocity v, and if we have net with area S, how to calculate the volume of water that passes through this net in 1 second. This volume can be calculated as surface integral of vector v, vector velocity of water, by ds. It will be flux of water through the net, and it is the volume that passes through the net during 1 second. And because this are similar expressions, and because of this we have name electric flux. Okay, do you have any questions? No questions. Okay. If there is no questions, we can continue. What is so special about electric flux? There is interesting property, very important property of electrostatic field that is known as Gauss law. Let's have a look at at closed surface. closed surface in volume. There is a closed surface, and there is some charge, electric charge QS inside the closed surface, and some charge QE, for example, outside the closed surface, outside this closed surface. And according to Gauss law or Gauss flux theorem, we can write. It's a pity, but we don't have enough time to prove this theorem. But if you are interested in, it is possible to find this proof in the internet or in literature. It is not difficult to find this because it is very well known. It is very well known from 19th century. So it is possible to find this. Gauss law or Gauss flux theorem. Gauss flux theorem. Integral form. According to this law or theorem, electric flux, this round means that the surface S is closed, and because of this I have written integral with circle, surface integral through closed surface of E ds is equal to Q S divided by epsilon 0, where QS is a charge inside the closed surface. So it is necessary to pay attention that there is no, in this formula, there is no charges from outside the closed surface. In this formula, we have only charges that are inside the surface S. It is very important property of electrostatic field. Very important property. And if there is some space distribution of charge, if we have charge density rho, we can write this Gauss law in the next way. 1 divided by epsilon 0 triple integral Vs. Vs is volume inside the closed surface. Volume inside this closed surface S. And here we have rho. Rho is charge density. Or density of charge dV. Okay, do you have any questions about this? Do you have any questions? In some important cases, uh, it is simpler to use Gauss law than this formula. So we will learn these cases. We will talk about them in future. And now we have to write this. We have to understand this. And maybe if you have some questions, you may ask them about this Gauss law. Okay, no questions. So let's continue. Let's continue. I need to clean some space. I need to clean some space on my screen. And maybe you can remember from your math courses, from calculus or mathematical analysis. Maybe you can remember Ostrogradsky-Gauss theorem or this formula. It is from calculus. According to this, surface integral E ds is equal to triple integral Vs divergence from E dV. Can you remember this from calculus or not?
Teacher, what is this?
Okay. Okay, this is a vector differential operator. Divergence or
Here is DIR, right?
DIV.
DIV. Okay, thank you,
Yes, it
teacher.
is DIV. Maybe I will look for correct translation of this. Wait a minute. I will look for correct translation into English. Divergence, the correct translation. It is divergence. It is divergence. So we can continue. Divergence. Divergence. It is kind of vector differential operator. Div E is equal to gradient operator multiplied by vector E, and it is equal to d partial derivative from ex by x plus d e y component by dy, and plus d e z by d z by d z by d z, and we can frame this. We can frame this and maybe it is necessary to remind that gradient operator, or operator of gradient, operator of gradient, it can be written d by dx I is order of axis x, d by dy yod, and plus d by dz k. E yod k are orders of coordinate axis in Cartesian system. Operator of gradient we have met before. But divergence we are meeting first time now. Okay, do you have any more questions?
Oh, teacher.
Okay, so let's continue. We can use this here. And we will obtain triple integral vs divergence of vector E, dv, and it is equal to triple integral vs rho divided by epsilon 0 dv. And from this equation we can get that divergence of electric field intensity is equal to electric charge density divided by electric constant. Divided by electric constant. Okay, is it clear? Okay, well, so let's continue. If everything is okay. If everything is okay, we can continue. And it is also Gauss law or Gauss flux theorem. Or maybe it is better. Maybe it is better to write this in more extended form. Because you may see this in the internet. You may find this in internet. We have so it is Gauss law or Gauss flux theorem. It is differential form. Of Gauss law. Differential form. Integral form of Gauss law is useful when we want to calculate electric field intensity that produced by known system of electric charges. And differential form is useful when we know electric field intensity and we want to calculate the density of electric charge. So both forms can be used. Both forms can be used for studying of electric fields and systems of electric fields. Okay, do you have questions? No questions. Okay, I will clean some space. I will clean some space on the screen. In order to write some more information. Divergence. Here we have divergence and operator of gradient. So if we have we can remember formula from our last lesson, from our previous lesson. We can remember that electric field intensity is equal to minus is equal to minus gradient from electric potential. It is from our previous lesson. It is from our previous lesson. And let's substitute this here. Let's substitute this here. We have divergence from electric field intensity. It is equal to minus operator of gradient multiplied by operator of gradient. No E, it will be phi. Electric potential, and it is the same. It is the same as modulus of operator of gradient, and it is the same as minus d2 by dx squared. It is necessary to open bracket here. D in second order divided by y second order plus d second by dz in second order. Multiplied by phi. And it can be written in short form. It can be written as minus phi. And what does this triangle mean? It is another vector differential operator. It is a Laplace operator. It can be. It is a short form of this. I will type this div grad. Maybe it is better to yes, it is better to write phi so Laplace phi is equal to divergence of gradient phi, and it is also equal to this scalar product, and from phi, and it is also equal to modulus second order in second order, and it is phi, and it is also equal d2 phi by d in second order by dx second derivative from phi by y, and plus second derivative of phi by that second derivative. And according to this, we can write that it is equal to rho divided by epsilon 0. And we have obtained Poisson equation. Poisson equation. Poisson equation. According to this equation, this operator of phi, Laplace operator of phi is equal to rho density of electric charge divided by epsilon 0. Divided by epsilon 0. Divided by epsilon 0. Epsilon 0 is electric constant. Maybe it is necessary to clean some space on the screen. Necessary to clean some space. And I will write that this delta is equal to by dx in second order plus d in second order divided by y in second order and plus d in second order divided by z in second order. Okay, do you have any questions about this? Because this subject is difficult to understand, is difficult to grasp, so it is necessary to learn it carefully, and it is necessary to pay attention to details. And if something is unclear, we will return to this, and we will try to remember this, because this formula we will use later. And now let's continue. I have to clean my screen. I have to clean my screen to continue. And before this moment of time, we have learned electrostatic field in vacuum. But we know that it is possible to produce electric field in media. And it is necessary to say that different media or different substances can be divided in three groups. These three groups are dielectrics, conductors, and semiconductors. Three types of substances. Maybe I'll type this. Three types or three groups, types of substances are dielectrics, conductors, and semiconductors. And semiconductors. What is the difference between them? The difference is in resistance. Dielectrics have very big resistance, and because of big resistance, they cannot conduct electric current. They have no free charges. That can carry electric current. Dielectrics. And in other way, conductors have a low resistance. They have many free charges, and conductors can easily conduct electric current. For example, you know that some metals or solutions of electrolytes or ionized gas are examples of conductors. And semiconductors, the third type, they are in the middle between dielectrics and conductors. In the middle between dielectrics and conductors is semiconductors. And we will start with learning of properties of dielectrics. We will study to learn electric properties of dielectrics. And what is some special properties of this? They have no free charges. Free charges are charges that can be easily moved. In space. But the dielectrics have so-called bound charges. What is bound charge? Bound charge is a charge that that cannot be easily moved from its place, but it can be but it can be moved just a little on a very short distance, And how can we understand? Can we understand these bound charges? What bound charges are? For example, all substances are consist of atoms and molecular but atoms are consist of positive nucleus and negative electrons around it. This is atom. So all substances have positive and negative charges inside them as part of atom. Moreover, some crystals are consist of ions. For example, salt. Salt, you know that salt is natri chlorus. Sodium chloride. This is sodium chloride. Sodium chloride. It consists of two types of ions. Sodium has a positive charge, and chlorus has negative charge. Because this atom attracts negative charge to itself, and because of this we have positive and negative charges, bound charges, positive and negative bound charges in the crystal structure of sodium chloride. And another example is water. Molecule of water consists of oxygen atom with negative charge and two atoms of hydrogen. It is water. So here we also have positive and negative charges. We have positive and negative charges, and pure water is also dielectric. Pure water is also dielectric. Maybe you know that water can conduct electric current, but it can do this. It can conduct electric current only if we have some salts. If we have some salts soluted inside in this water, but pure water is dielectric. Pure water is dielectric. Maybe you know this. If you don't, I have just told this. So do you have any questions about bound charges in dielectric? No questions. Okay. If you don't have any questions, it is necessary to take into account that that the whole dielectric is electrically neutral. So it means that it has the same value of positive and negative charges, and whole dielectric is electrically neutral. So we can consider pairs of positive and negative charges like this. Qi minus Qi minus Qi minus Qi and plus Qi. Plus Qi, and Li is vector that connects that is written from negative to positive point charge. This pair of positive and negative charge is called electric dipole. If the modulus of vector Li is small, we can consider pair of 2 point charges as electric dipole. And electric dipole may be described with so-called dipole moment or electric dipole moment. Pi is electric dipole moment. Electric dipole moment, it is equal to electric charge multiplied by vector L. That is shown on the picture. So it is electric dipole. And electric dipole moment. Electric dipole moment. It is here. So we can frame this. Okay, do you have any questions about this? So positive and negative charges, bound positive and negative charges inside dielectric can be united or can be considered as electric dipoles. And when we have electric dipole, and if we want to calculate the sum of electric dipoles, we'll have 0. So if we have dielectric, in vacuum without any external fields, we have 0. because we have different directions of dipole moments. We have something like this. Dipole moments are oriented chaotically. So because of this orientation, because of different orientations, many different orientations, we have zero in this sum. But what will happen? What will happen if we put dielectric inside external electrostatic field? What will happen? Let's have a look at single dipole inside this field. Inside this field, there will be next situation. Plus qi minus qi minus qi. And now I will show here external electrostatic field. Let's make it homogeneous. External electric field we have here. This is external electric field. And we have already learned that that there will be electrostatic interaction between charges and electric field. There will be electrostatic interaction. Electrostatic interaction that can be shown in this way. Phi I and minus phi I. Minus phi I. And we know that we know from our previous lesson, we know that this force can be calculated by formula. Qi multiplied by EI. Multiplied by EI. So we can see that external electrostatic field tries to orient electric dipole in the direction of itself. And because of this orientation, the situation will change. The situation will change. Because of this orientation, there will not be zero. There will not be zero. Because we will have more dipoles that are oriented in the direction of electrostatic field. Okay, is it clear? Do you have any questions? Do you have any questions about this? No questions. Okay, and can you hear me?
Yes, teacher.
Yes, okay. That's great. That's great. And this orientation of dipoles of bound charges inside dielectric is known as polarization. This known as polarization. Polarization is orientation of electric dipoles inside of dielectric. And it can be described with polarization density. Polarization density. Polarization density. Polarization density. Polarization density. Vector of polarization density is equal to sum of dielectric moments inside some volume delta V. This is polarization density of dielectric. Polarization density. It is polarization density. And there is a question. How to calculate polarization density? How to connect this value? With electric field intensity? That is here. How to connect them? According to the experiments, for many types of dielectrics, we have quite simple expression. For many types of dielectrics, but not all of them. But for many types of dielectrics, we can write P is equal to kappa epsilon 0 multiplied by E. Where kappa is a property of dielectric, and it is called. It is better to type this is electric susceptibility. It is a property. Of chosen chosen type of dielectric. Property of material. And it depends on dielectric. It is necessary to take into account that sometimes such simple expression cannot be used. cannot be used. For example, it cannot be used. It cannot be used for dielectrics that are not isotropic. So it is for isotropic dielectrics. Maybe I will write this. For isotropic dielectrics. For isotropic dielectrics. Isotropic dielectrics without dielectrics that don't have memory effect. That don't have memory effect. We can use this simple formula. We can use this simple formula for isotropic dielectrics that don't have memory effect. And what is memory effect? Memory effect means that electric susceptibility kappa depends on polarization that dielectric has had in previous moment. So kappa depends on polarization in previous moment, not only on present moment. It also depends on polarization in previous moment. But we have no time to learn memory effect. It is difficult, and we will not learn anisotropic dielectrics. So we will learn only isotropic, and it means that kappa is a simple number. For dielectrics that are not isotropic, it is necessary to use three-dimensional matrix. Instead of simple number. But we will learn only this simple case. Okay, do you have some more questions about this? No questions. Okay, so I need to clean some space. I need to clean some space on the screen. Oh, here we have connection. Here we have connection between or dependence between polarization density and electric field intensity. And how to connect bound charges and polarization density. It can be connected with Gauss law. So we also have Gauss law for polarization density. Gauss law for polarization density. Gauss law or Gauss flux. Theorem for polarization density. For polarization density. Integral form. Integral form. This integral form. According to this theorem, surface integral P ds P ds is equal to minus q s. This means bound charges inside closed surface. Bound charges inside closed surface. And it can also be written as triple integral of density of bound charges dV. dV. Density of bound charges. And like it was for Gauss law for electric field intensity, this Gauss law can also be written in differential form. It can also be written in differential form. So let's do this. Let's write Gauss law for polarization density in differential form. Gauss law, Gauss flux theorem for polarization density differential form. Differential form. It is differential form. Divergence of P, divergence of polarization density, is equal to minus density of bound electric charge. Density of bound electric charge with minus. Okay, do you have any questions about this? No questions. No questions. Okay. Okay. So let's have a look at dielectric in vacuum. in vacuum, and inside this dielectric we have some bound charges, and let's draw some closed surface, let's draw some cylinder on the surface of this dielectric. This cylinder is infinitely small. This cylinder is infinitely small, and the base of cylinder is has area ds. And let's use this. Let's use this to this cylinder. Let's use Gauss law to this cylinder that we have drawn. Here we have polarization density vector. For example, it can be written like this: vector P, polarization density. And let's use this theorem. According to this, we have P multiplied by ds. There is no integral because closed surface is infinitely small. This cylinder is infinitely small, and because of this we don't have integral here. So it means it is equal to P n ds. Pn is a projection of polarization density vector on the normal direction. On the surface of dielectric. And according to Gauss law, it is equal to bound charges inside this cylinder. And what can we say? What can we say about charges? About charges on the surface of the dielectric, so-called surface bound charges. If the charge inside dielectric is plus, we will have negative charge on the surface. And if we have negative charge inside dielectric, there will be positive charge on the surface. So it can be written as minus sigma ds, where sigma is surface density of bound charges. So we have sigma ds. So Pn ds is equal to sigma ds. is equal to sigma ds. And we can divide left and right sides by ds, and we will obtain that Pn is equal to sigma, and sigma is surface density of bound charge. Surface density of bound charge. Okay, do you? Yes.
Sorry, I cannot distinguish these two symbols. This is rho, right?
Yeah, this is rho, and this is sigma. So
Sigma. Okay.
this is
Oh, I understand. Sigma, this, right? Yes.
yes, sigma. Sigma, it is a Greek letter. Sometimes we use them. In order not to repeat the same signations. For different values. And so it is sigma. Is sigma. Okay, do you have any questions about this? Okay, if there is no questions, I think we can finish for today. We can finish, and I hope to meet you tomorrow. And we will do some more exercises.
Okay, teacher, have a nice day. See you tomorrow.
Okay, have a nice day.